Today's class, we want to talk about another topic called area under a curve. For area under a curve, we're going to consider values like you having something of this nature. If you have a graph of this nature, and probably you're having something like this, you observe that under this curve, under this graph for the x-axis and the y-axis, you can have partitions. That's the word, partitions. That's in different parts, partitions of this nature. And these partitions, you may assume that this is x1, x2, x3, x4, x5, x6. Now, how do I get this particular one if I decide to bring it out? If I decide to bring this out, this is x2 and this is x1. So if I want this, I will get the distance from here to here becomes x2 minus x1. That's my value. And that value, you always call it change in x. Now class, that is for area. What about a situation where I have something of this nature? If I have area, maybe I have area of this nature, I have something like this, I have this, I have this, I have this. Now, 1, 2, 3, 4, 5. And probably I have the last one, which is the sixth one. Now if I decide, I can look at the points here. 1, 2, 3, 4, 5, 6, 7. Now if I look at these points, it's easy for me to say that if at this point I'm having value of y-axis and this value here is x-axis. Now it's easy to calculate the area of this area under this graph. It's easy. Now let's not start with curve. Let's talk about the graph itself. Now area under the graph, calculating that is easy. Let's assume the curve that was given, maybe on a teeth, it touches here, it touches this point, it touches this point, it touches this point. This is a curve now. Now, if this is a curve, the teeth for the curve, you can have values now. Let the curve be equals to x squared minus 3. Let's assume this. If it's x squared minus 3 as the curve given, that's not an issue. That shows that fx, the function of x, is also x squared minus 3. Now, if that's the case now, it's simple and easy for us to assume that if these partitions are done in 1, in 2, in 3, in 4, in 5, in 6, and in 7, you observe that for my value of f1, what I will get is 1 raised to power 2 minus 3, which will become 1 raised to power 2 minus 3 automatically will give me 1 minus 3, which is minus 2. If I get 2, I will get the same value as 1 raised to power 2. They are already partitioned. That's 2 raised to power 2 minus 3, which is equals to 1. I can decide to start from here depending on my partition. But I decide to start from 1. So my f3 will give me 3 squared minus 3, all from x squared minus 3. 3 squared minus, that's 9 minus 3, that becomes 6. And my f4 gives me 4 raised to power 2 minus 3, and that becomes 16 minus 3. Surely that will be 13. Now, the way the values taking them in order, if you add everything together, the sum total of everything you get here is equals to area under the curve. Take note of that. That's the first thing. So by the time you take all the functions together, you sum it together, you get area under the curve. But that's that. That's when you are partitioning the area under the graph. But when you are not partitioning, you're going to take this from me. Area under a curve is given as A is equals to the integral BA y dx. So please, class, you must take note of this. With this, you can calculate any area under any curve. The value of y is the curve. So where y is the value of function of the curve. So please take note of this. So this remains. This is the upper limit and this is the lower limit. The upper limit and this is the lower limit. Always remember that. So area of a curve or area under a curve is equals to the integral of y dx. But when you are partitioning, you can take this and partition to get it. So the sum total, whatever you get, f1, f2, f3, f4, f5, f6, x7, by the time you sum everything together, whatever you get is still the same value as area under the curve. But to calculate area under the curve in direct values, it's A, is integral of BA by D. So I'll take an example with respect to this. Now take a look at this curve, for example. If I have this curve, for example, maybe I have something of this nature. I have something of this nature. I have y, I have x. For example, I have a curve that moves like this, and I'm asked to find the area under the curve, and maybe I have to shade the area. I have to shade the area. If I have to shade the area, maybe at this point, this part here is the value of 3 and this is the value of 1. 1 lower, 3 higher. If I have something like this, this is the curve. But funny enough, if this curve itself has a value of y equals to x squared plus 2. If I have a value of this, x squared plus 2 as the curve. The value of this curve is x squared plus 2. But within the range or partition range of 1, 3. The curve is y equals to x squared plus 2. But within the partition range of 1, 3. Now let's do this. Within partition range of 1, 3. Let's go. 3 is greater than 1. So because of that, we have our formula goes back. A is the integral BA y dx. Now how do we do this? So the area now becomes, what's the highest? The highest is 3. The lowest is 1. So you call it upper limit, lower limit. So from there, we'll still talk about that under definite integral. But from here, what's the value of y? The value of y is x squared plus 2 dx. So what we're doing now is to integrate the value. We already used to integration. I want to integrate the value of x squared plus 2. So integrating x squared plus 2, how do you integrate that? Integrate x squared plus 2 will automatically give us x 2 plus 1 over 2 plus 1 plus 2x plus c. That's the value. So from there, I have, that gives me x raised to power 3 over 3 plus 2 plus 1 is 3. 2 plus 1, 3. Now plus 2x. So you have 2x plus c. That's your value. Now, please take a bracket on it. The one at the top will be 3 and the one down will be 1. Where did that come from? BA, 3, 1. So now from there, let's take our calculation. That becomes, or take a value of the fact that I'm going to substitute the value of 3 first. And later I'll substitute the value of 1 and I'll subtract. You can do that straight. If you want to. Now let's take a look at this. The first one, let's put 3 first in every value of x. So that will be 3 raised to power 3 over 3 plus 2 into bracket 3 plus c. We have that minus. It's not time for 1. So what do you have? 1 raised to power 3 over 3 plus 2 into bracket 1 plus c. So this is for 3 and this is for 1. So you substitute 3 first minus when you substitute 1. So let's go. That gives us 3 raised to power 3. That should be, surely will be 27. You divide it by 3. Surely that becomes 9. 2 times 3, that's 6 plus c. Minus. That's the same thing as 1 over, I take the bracket still, 1 over 3 plus 2 plus c. So when you open this bracket, you have 9. 9 plus 6 surely will be 15. That will give us 15 plus c. 15 plus c minus the value of 1 over 3. Let's take the 1 over 3 and 2. So 3 times 1, 3 times 2 is 6. Plus that is 7 over 3. So 7 over 3 minus c. So the c will cancel c. That disappears. That becomes 15 minus 7 over 3. So in context, let's finish this up. So if you have 3 times 15, so surely you have 30, 45. So 30 for that's 45. 45 minus 7. You remove 45 from 7, 7 from 45. You have the value of 38. So automatically that becomes 38 over 3 units squared. Now, the squared comes from the fact that area is measured in centimeter squared, meter squared. So normally you're supposed to have a value unit, but it becomes unit squared. So when you take this down, so this is the value of the area under this curve, which is partitioned 1, 3. Good. Now we've talked about that. Now we'll take another example. That is one more example on area under a curve. Now let's consider these two. You have a situation where you have a curve that is of this nature, and you have something like this, maybe of this nature. Let's try to see something like this. Maybe you have something like this. You have something like this. This is on the negative side of the equation. Maybe here you have minus x plus x plus y minus y. Now if you're having something like this, it's possible for you to have the area under the graph partitioned in the form that this is the 0 point and this 0 is greater than that, this is greater than this. So automatically, if I'm having minus 1 here and here I'm having minus 4. If I'm having situations like this, I cannot say I'm calculating area under a curve. Area under the curve. Let's continue with this. So this it's easy to set in that you can use the same formula which says that A is integral BA y dx. So with this, let's substitute. We know the partitions. What are the partitions? Minus 1, 1. But funny enough, minus 1 is greater than minus 4. You should understand that. Minus 1 is greater than minus 1. Surely, you prefer to owe somebody 1 naira than to owe the person 4 naira. Although, that is for mathematicians. Accountants will disagree with that anyway. They will tell you that they prefer to owe 4 naira than to owe 1 naira. And that they can make money with that 4 naira. So probably that's why mathematicians are poor. Now, that's that. Let's continue. You have a certain value of this nature. For your partition, that becomes, the area under the curve now becomes minus 1 at the top, then minus 4 down. Because, but the curve itself, let's assume that the curve is y raised to power y is equals to x squared minus 3. Let's assume that. So if it's partitioned like this one, that's y. That's for the value of y. That becomes y squared minus 3. Then you have dx. Let's try this. So automatically, my area now becomes whatever I get from this place. If I differentiate, integrate this, integrating this will give me, this is the value of x. If you integrate this, that becomes x 2 plus 1 over x 2 plus 1 minus 3x plus c. So that gives me x3 over 3 minus 3x plus c. But beautiful enough, it's simple. So with this, we can now take our bracket and find you have minus 1 at the top and you have minus 4. So whatever you substitute here, what you end up getting is the value of A, which is the value of the area under a curve. And what's the value of the curve? The curve still remains y is equals to x squared. So if, for example, you are having a situation where it tends to be elliptical, you can have values like running. Maybe this is shaded, and here you are having 3, and here you are having 8. If you're having something like that, and the curve y is equals to x raised to power 3 plus 4x. If you're having something like that, what do? What will be the area? The area becomes 8 at the top, 3 down. What's that? X raised to power 3 plus 4x dx. So when you integrate this, surely the integration of this will give us x3 plus 1 over, that's x4 plus 4 plus, what do you have there? 1 plus 1, that will be 2. Then 2, that will be 2x squared plus c. So by the time you substitute this, 8 and 3, 8 and 3, whatever you substitute 8 first, you get the value. Substitute 3, you get the value. You subtract the value you get from 3 away from that of 8. What is left will be the area under the curve. So, class, we've come to the end of area under a curve. So thank you very much. We'll meet in other classes.